Welcome to The Explainer. Today we are cracking a classic case of mathematical mistaken identity. And our main suspect? These two little vertical bars right here. They pop up everywhere in math, but what they actually mean, well, that can change in a big way. So let's get into it and solve this thing. Okay, so check this out. On the left, you've got those bars wrapped around a single number, -3, and boom, you get +3. Simple enough. But then on the right, you see the exact same bars around a whole grid of numbers. That's a matrix. And suddenly, it's this whole AD minus BC operation. It's the same symbol, but they're doing completely different jobs. So what is going on? Yeah, this is one of those things that trips a lot of people up. But trust me, once you see the logic behind it, it's all gonna click. So let's play detective here and look at each case one by one. All right, first up is our old friend from algebra class, the absolute value. This is probably the first place any of us ever saw these vertical bars. The easiest way to think about absolute value is just distance. That's it. It's simply asking the question, how far away is this number from 0 on the number line? It couldn't care less if you go left or right, positive or negative. All that matters is the distance. Right. So whether you're standing at the number 3 or you're all the way over at -3, you are still exactly 3 steps away from 0. And here's the key thing. Distance can't be negative, right? So the answer you get from an absolute value is always going to be positive or 0. And this whole distance idea is why when you see absolute value in an equation, you usually get 2 possible answers. I mean, if I tell you the absolute value of some mystery number is 5, well, that number could have been +5 or it could have been -5. Both are 5 units away from 0. Okay, let's switch gears now and talk about our second subject, the matrix. It definitely looks a bit more intimidating, but I promise the logic for what those bars are doing is just as clear once we break it down. So first things first, a matrix is not a number. It's a totally different kind of mathematical beast. It's really just an organized grid of numbers, kind of like a little spreadsheet with rows and columns that keep all the information nice and neat. Now, here's where the plot thickens. Those vertical bars, they only get this second special meaning when you put them around a square matrix. That means a matrix with the same number of rows as it has columns, just like this little 2x2 example here. When you see bars around a square matrix, they are not asking you for a distance. Nope, they are a command, an instruction to calculate one very specific, very important number that tells us something fundamental about that matrix. And that special value has a name. It's called the determinant. You'll see the word scalar value there. That's just a fancy math speak for a single number, not a whole grid. And for a simple 2x2 matrix, the calculation is super straightforward. You just multiply down the main diagonal and then subtract the product of the other diagonal. Simple formula, but it holds a really powerful idea. So why on earth do we care about this number? Well, here's where it gets really cool. In geometry, you can use matrices to describe transformations. Things like stretching, squishing, or rotating a shape. The determinant tells you exactly how much the area of that shape is going to change after you transform it. It's one number that packs in a ton of information. Okay, so we've looked at the evidence from both sides. We've got the absolute value, which is all about distance for a single number, and we've got the determinant, which is all about a scaling property for a square matrix. Let's bring it all together and close this case. And the mystery is solved. The solution, as you can see, is all about context. It's about what is inside the bars. If it's a single number, a scalar, you're looking at absolute value. Just think distance. If it's a square grid of numbers, you're calculating the determinant. Think scale factor. And look at that last point. Absolute value is always positive or 0, but a determinant, it can be positive, negative, or 0. And each of those tells you something different and important. This whole thing is a perfect example of a bigger truth in math. Symbols aren't always one of a kind. Just like the word lead can mean to be in front, or it can mean heavy metal, the meaning of a symbol in math completely depends on how and where you're using it. So the big takeaway here is to always look at the context. It's a great reminder that math really is a language, and just like any language, context is king. And that kind of leaves us with a fun question to chew on, right? Now that you know about this one, what other math symbols have you seen out there that are pulling double duty? What other mathematical synonyms are hiding in plain sight?